For our last talk today, we're really excited to have Professor Stefano Allesina from the Ecology and Evolution Department at the University of Chicago. And Stefano works on a lot of interesting questions in theoretical ecology, particularly things like stability of ecological communities. And we'll be talking about equivalence between ecological and evolutionary game models to study global stability of ecological communities.
Thank you. Yeah, thank you for sticking around. So my talk would be of the foundational type like hardness, and my starting point is really like the two types of equilibria that we have in symmetric metrics game. So we have Nash equilibria, right? Imagine that P star is a Nash equilibrium, then this is the best response to itself. So nobody can do better by deviating from this. And then we have a refinement of Nash equilibria that is an evolutionarily stable strategy, which is a Nash equilibrium that is also uninvasible from any other point. When this Nash equilibrium is in the interior of the simplex, meaning it has only positive components, then the condition for an ESS is actually quite simple, and it's just another inequality saying that playing P star against P, you're doing better than P against itself. And so I put these two conditions here because they will come over and over again. And then this simplification for ESS actually comes from the idea of indifference in Nash equilibria. So if I have a Nash equilibrium and I have two strategies that I'm playing with non-zero probability, then they need to have the same expected payoff when the state of the system is P star. Which means what? That if I'm playing all the strategies, then A times P star needs to be a constant vector, right? And therefore, if you play any strategy, right, any P against A P star, right, you will always get the same number. So in this case, we have equality across, and that's why this condition simplifies. So this is about Nash equilibrium. Then this was already put up before, like by Arne and other people, right? Like the idea of evolutionary stable strategy is actually coming from biology, right? It's a biologically inspired concept. And this is due to George Price and Maynard Smith. And so I knew that George Price, whose life is really incredibly interesting. There is this book, The Price of Altruism, that I strongly recommend, even though if you can take the difference between these two numbers, it doesn't end well. But I knew that he was a student of the University of Chicago, where he got his PhD as part of the Manhattan Project in 1946. I didn't know that also Maynard Smith had connections to U Chicago. And in fact, he developed this theory of evolutionary game theory when he was in a sabbatical at the University of Chicago in 1970. And then I was listening to this interview that then I immediately said to all my faculty, because this tells you how much he enjoyed Chicago. The only thing you can say for Chicago is that it's so awful. There is nothing to do there except work. So a lot of like the development of evolutionary game theory is due to the fact that the University of Chicago had a motto back then, where fun goes to die, right? And for better or worse, I don't think it is true today, just saying, but it's funny. And there's a whole backstory. And I was able to talk with people who were around when this happened. And I can tell you later because it's, it's not a good story. So evolutionary stable strategy, resistance to mutant invaders, already embeds, and in fact, all of evolutionary game theory from the name points to some idea of dynamics, right? Because you have to have the invader, they need to be excluded, so something has to happen in time. And so it's not a surprise that after a few years, people started studying dynamic versions of these games, especially the replicator equation, which was introduced in 1978. And what is nice is that Nash equilibria and evolutionary stable strategies are concepts that are defined on the static version of the game, right? So you can study them just in the classic sense of game theory, but they also have a special meaning in the replicator equation. And this is like what it's called the Folk theorem, that says that a Nash equilibrium is also an equilibrium of the replicator equation, which makes a lot of sense. The converse is not necessarily true, which also makes sense. Imagine that you're in the simplex, then any corner of the simplex would be an equilibrium of the replicator equation, but they do not need to be a Nash equilibrium. And in fact, I come from Lotka-Volterra, and we already discussed the back and forth between replicator equation and Lotka-Volterra. In Lotka-Volterra, a Nash equilibrium would be a non-invasible equilibrium, right? So an equilibrium that can resist invasions from rare species. Then ESS also has a special meaning in the sense that if we have a point that is an evolutionary stable strategy, then it is a globally stable, globally attractive equilibrium in the replicator equation. The converse is not necessarily true. And this is not as natural as we would like, right? And in fact, this led to some sort of soul searching in evolutionary game theory, because how can something be dynamically stable and yet be invisible, right? It doesn't make too much sense, but you can find it, in fact, in the first paper on the replicator equation, Taylor and Yonker, 1978, they have an example of this matrix. And you do the dynamics. Here I'm starting from different starting points of the circles, and you can see that we spiral toward a globally stable fixed point, and yet the areas in blue here are the ones in which this inequality would not be satisfied. So this point is dynamically globally stable, but not evolutionary stable. Okay. Right. So my talk is just trying to take another look at this problem. Okay. And the way I want to do this is by equivalence. And by equivalence, what do I mean? I want to write two models, right? Two replicator equations. One that is in P and with the payoff matrix A. The other one is in Q with payoff matrix B, such that I can move back and forth between these two systems via homeomorphism. So I map all these trajectories to those trajectories and back. And therefore, because it's a homeomorphism, it can change the geometry, right, of the system, but not the topology of the system. And as such, the number of fixed points, their stability, the type of dynamics is maintained by this transformation. And what I want to show you is that there's two of these classes of equivalence that are well known, and they've been known for a while, but I think they're underappreciated. So let me start with the equivalence one, which is the following. I can map P into Q, so I have exactly the same dynamics, but I have two different matrices. One is my matrix of payoffs A, and the other one is a matrix of payoff they obtain from A by adding a possibly different constant to each column, right? This doesn't change the dynamics, right? So you can take B as being a rank 1 update of A with constant columns, and you will have the same dynamics. So these two replicator equations will have the same stability, et cetera, et cetera. This is the most well-known. The second one, it's called the projective transformation in this book. And Arne already told you about this book. This book is, called the Bible in my lab, right? Because exactly as the Bible, there's an answer to anything that you might ask. But exactly as the Bible requires a lot of interpretation, and especially very fundamental results, as Arne showed already, are given as exercises. So this is the exercise 7.1.3, where they say, do this as an exercise. We call it the projective transformation. And the idea is the following. We take a vector P, right, that it's in the simplex, and now we weight every entry of this vector by a different weight. And then we would get something that doesn't sum to 1 anymore. So we normalize by the sum of all the weights times their things. So this transformation maps the simplex into the simplex. One way to think about it is imagine Pi is the proportion of individuals of type I, and W is the weight associated with each individual, then Qi would be the proportion of weight. Clearly, the proportion of weight or the proportion of individuals, if one goes to an equilibrium, the other one needs to go to an equilibrium as well. Then you can do a little bit of linear algebra, which you should do the exercise yourself, right? But what you find is that this is also a transformation of the original matrix, and what we'll end up doing is multiplying each column by a constant, right? So we're rescaling each column. Another way to think about this is like we're having these payoffs in different currencies, right? The first column is in dollars, the second in rupees, the third one in euros, and you would get something like that. Importantly, by doing this transformation, we can move the equilibrium wherever we want in the interior of the simplex if we have an equilibrium in the interior of the simplex, which is the only case I'm interested in. So that's exercise 7.1.3. Now, we're going to use these two classes of equivalences to first simplify the calculation of when is an ESS an ESS, and then we're going to see later. So this is another exercise 6.4.3. This one I felt generous and I did it for you on the board. And so the idea is to simplify the calculation of when is a point an ESS. And so you take the definition of an ESS, and what you can do is you can write any vector P in the simplex as p star, right? The point in the interior of the simplex plus a deviation. Now, because both p and p star both sum to 1, right? Then if I sum the left-hand side and sum the right-hand side, then necessarily epsilon, these deviations must sum to 0, right? If something goes up, something else must go down. And so you just rewrite all these as functions of p star and epsilon, and then some terms fall out. And then because of indifference of Nash equilibria, then I have epsilon transposed times a vector that is constant, then it has to be 0 as well, right? So then you end up with this simpler characterization that you only care about the metrics and deviations, right? So if you could show that for every epsilon such that it sums to 0, so in the space that is tangent to the simplex, any vector in the space that is tangent to the simplex, this quadratic form is negative, then you have an ESS. This is like a little too advanced for me. I'm not a good mathematician, so I want to do like use equivalence 1 to make it a little simpler, and especially get rid of the tangent to the simplex. And the way I'm going to do this is I choose a particular rank 1 matrix, right, to update my matrix. And what I'm going to use is for gamma, I'm going to choose the negative of the last row, such that when I sum these two matrices, the last row is composed of all zeros, right? So now I had a square matrix, and now I have another square matrix. This is of size n minus 1. I will call that M. I will have a vector of length n minus 1, R. This, by the way, is exactly how do you go from the replicator equation to Lotka-Volterra, right? So this would be a Lotka-Volterra model with matrix of interaction M and growth rate vector R. Now that I'm in this situation, I can think of any vector that sums to 0. I can write it in this following way. I write n minus 1 numbers that can be whatever they want, and then the last number, because they have to sum to 0, necessarily has to be the negative of the sum of the previous numbers. Right? So I write epsilon as z1 to zn minus 1, and then the negative of the sum of all these entries that I had before. But now my epsilon transpose a epsilon becomes something much simpler, right? It's a quadratic form in z, and where z is an arbitrary vector now. So this is negative in the space tangent to the simplex if and only if this matrix, or rather the symmetric part of this matrix, because it's a quadratic form, is negative definite. So now I can open any book on linear algebra and say something intelligent about the distribution of the eigenvalues of this matrix. So we use this first equivalence, this first class of equivalence, just to simplify the calculation of is a point an ESS or not. Now, if you have to take anything from this talk, is this sentence. The notion of an evolutionary stable strategy is not closed under transformation 2. Which means what? That I could have a game in which I have an ESS, I apply this projective transformation, and I break the ESS. Okay, that's the negative way to look at this. More positive way of looking at this is I have a game where I have an equilibrium that is not an ESS, and I can find an equivalent game in which this is an ESS. So because I am like, I see the glass half full, I'm going to take the second perspective on this. So I'm going to show you how you can do these ideas, like how can you apply this idea exactly to the matrix that was proposed by Taylor and Yonker. First, we're going to show that the point is not an ESS in this game, right? So what we do, we take this matrix, subtract from each column the last coefficient, right? And so we remove 1 from here, 4 from here, and 3 from here. Now we identify this matrix, right? M, that is this square block here, this vector R. Then we compute M minus 1 R transposed. It's this matrix. We take the symmetric part. It's this matrix. We compute its eigenvalues. This is a symmetric matrix. Will be 2 real numbers. One of them is negative. The other one is positive. So this is not an ESS. Right? This is how we apply the calculation that I showed you before. Now we're going to look for a transformation of this matrix. And what we can do is fundamentally take each column and multiply by a positive constant of our choice. And so my choice is 1, 2, and 1. So I'm going to keep like the first column and the third column the same as before. but I'm going to double all the elements of the second column, right? This is exactly this type of transformation, right? We stretch one axis of the simplex and then we renormalize. And then I do exactly the same operations that you can see the first and the third column are the same as before, but the second has changed. And therefore, M has changed, and R is the same as before. I get this matrix, and now my eigenvalues are all negative. And therefore, this is an ESS, right? But if this is an ESS, it means that these trajectories in the second model are always converging to the equilibrium, which means that in the first model, you have proven global stability via equivalence. Right? So that's like the logic of this. I'm going to tell you something later about this. It's like how to be lazy. Geometrically, what we're doing is this, right? We took this simplex, and we didn't like it because we had these blue areas. And then we fundamentally stretched one of these axes, right? We renormalized, reprojected on the simplex, and now we have everything follows this inequality, and therefore the fixed point is globally stable. But if this point is globally stable, then this point is globally stable as well. Okay? So then this tells you the idea that we can find, sometimes we have something that is dynamically stable, but it's not an ESS, but maybe we can find another system that is equivalent to the original system in which this is an ESS. And this is like almost resolving the problem. And so in practice, what we have is like we take a matrix that has 0 on the last row, and there's an equilibrium in the interior of the simplex. If there exists a V greater than 0, such that the symmetric part of this matrix, M rescaled by V minus 1 R transpose is negative definite, then P star is globally stable. So that's all I wanted to say about this problem, but I want to just say something about these equivalences and how can we maybe use this to expand the idea even more. So what we said is like, as a summary, two replicator equations A and B, if they can be written in this way, right? B is a rank 1 update of A, maybe with all the columns rescaled by a positive constant, then defines an equivalent game. And then we can use equivalence 1 to simplify the conditions to check whether a point is an ESS. And then we can use the second equivalence to try to expand the reach of this ESS. That's like the way I think about this is it easy to find the Lyapunov functions? It's not easy, right? Steve Strogatz in his book has this nice quote that I like that says that divine inspiration is usually required to find a Lyapunov function for something that you want. And so because I have no divine inspiration whatsoever, I'm probably the person with less divine inspiration in this room, what I want to do is, instead of coming up with a new Lyapunov function for my system, I massage my system into something where I can use the Lyapunov function that I know already. Right? So that's basically my idea of being lazy about Lyapunov functions. And now, will this always work? That is a very interesting question, and it is a question that comes with two parts. So these, I gave like this talk maybe a year ago. Some of the people in the room already seen this talk a year ago, or a year and a half. And then people ask me, can this be proven? And I'm not a mathematician, so I'm like, yeah, maybe it could be proven, but I don't know how to prove it. Then I spent, like quality time with this problem, like in the past summer, and I was able to prove that this is the case for n is equal to 3, right? It's a very pedestrian proof. And what I found out that is interesting is that this is going to be true. So any replicator equation with a positive equilibrium that is globally stable can be mapped into another replicator equation where the globally stable equilibrium is an ESS, always, unless the game is degenerate. So if the game has two Nash equilibria, the number of Nash equilibria is typically odd. If it has two Nash equilibria, then it's not true. Right? It's still globally stable, but you need to use LaSalle or things like that. Is this going to be true for n is equal to 4? I think that either the answer yes, it's interesting. The answer no is also interesting, especially if the answer no comes with something else, right? That says there are maybe other classes of equivalence, right? These two you can find in the book of Bauer and Sigmund. Are we sure that these are the only two ways to map a replicator equation into another replicator equation by changing variables or by doing this type of operations? Are there generic classes that apply to all systems like the one that I showed you? Or maybe there are specific classes, right, that only apply if the matrix has certain properties? That, I think, is an interesting question. And then, because of the relationship between replicator equation and Lotka-Volterra models, you can show that this approach improves over the candidate Lyapunov function for Lotka-Volterra systems that has been used since 1976. So when I was born, like the Lyapunov function for Lotka-Volterra models was also born, and I was incredibly annoyed that no one had made any progress in this problem in 50 years, so that's why I wanted to study this problem. Thank you.
I guess we can do, if anyone has any questions, and then we'll also do a Q&A session with all the speakers from the afternoon as well.
Okay, so that blew my mind. Okay, clarifying question. When you say an ESS is globally stable, that's for an interior ESS specifically, right?
So an ESS is always globally stable. I think like any ESS, yeah, it's a globally stable equilibrium of the dynamics. It's only if it's in the interior that then you can do these simple theoretically, for an ESS, you need two inequalities, right? And they need to have a relationship. When it's in the interior, this becomes a simple inequality. And then you have this other test that I had, this thing is lower than zero for every, say, this is true only if P star is in the interior. Otherwise, you have to do something more complicated.
I'm still a little confused about that, but my bigger question, you had a positive spin on your result, which is that you can use it to find globally stable equilibria, but it feels like a negative result to me in that, like, do we need to reconsider the utility of ESS if it's not preserved under this natural?
Yeah, we're not the first people to ask this question. There are entire books on, shall we redefine ESS as exactly like global stability? So we should weaken in a way like the notion of ESS, or shall we make it stronger? This debate has been going on for 50 years. My thinking is maybe we're looking at this problem in the wrong space, right, in a way, right? So that this is saying, oh, yeah, there is a natural setting to play this game, right? There is a natural geometry for this game, and we're looking at this in the wrong geometry. So that's the more positive spin that I can come up with. But yeah, it's interesting because this thing, physicists have this word that I have trouble pronouncing, gauge, right? Like that these things shouldn't matter, right? Like what do you measure? Like, do you measure the number of legs of an individual, the number of eyelashes, or the weight, or the number of individuals? Who cares, right? Like it doesn't matter, but it matters. So that is the negative part, I would say.
Yeah.